This conference will now be recorded.
All right, hello everyone. This is Brian Gockel, Office of Observations, welcoming you to this week's Satellite Book Club seminar series. The title of today's talk is Satellite Data Assimilation, a Catholic, that's with a small c, perspective. Our presenter is Jim Yo, NCEP coordinator for both observations and science and technology integration. And Jim also holds the title of Chief Administrative Officer for the Joint Center for Satellite Data Assimilation. Also today, we've got volunteer help from Steve Flegel. Steve, thanks very much for joining us. Steve's the Sioux from WFO Aberdeen, South Dakota. And we appreciate both Jim and Steve volunteering to help us put today's presentation together. Just a few reminders before we get started. You probably heard the prompt. As usual, we're recording it, today's session. And also, as usual, we'll be having a Q&A session at the end of the presentation. And again, we'll use the chat to capture your questions. So please post your questions in the chat room. And Kashad, the TOWS team here, Lee, they're going to make sure that we get them to Steve so your questions can be addressed. We today, as always, looking for future presenters. Please contact the TOWS team. There's contacts herein for you to do that if you're interested. We'd love to hear from you. And the training team can help you create the materials both for your briefing as well as for training purposes afterwards. And Brian Mata is always with us on these calls and can field your questions regarding that. A few thank yous to the TOWS team. Kashad Bowman here. Thanks for putting this together and getting me primed as well. Office of the Chief Learning Officer, GOES program, JPSS, and of course, all of you for joining us today. So, introducing Jim Yo. Jim received his BS and PhD degrees in physics and then went on to do 3 years of postdoctoral research on wind, waves, and turbulence using Doppler radar and Lidar at the Max Planck Institute for Aeronomy in Germany before joining NOAA NESDIS in 1993. At NESDIS STAR, Jim worked on the Doppler Wind Lidar mission formulation and GPS Radio Occultation data analysis and became deputy director of the center in 2005. He then joined NESDIS, the NESDIS Post Data Exploitation NDE project, which is where I had the pleasure of first meeting Jim. He was with NDE for several years before returning to the Joint Center as a Chief Administrative Officer when he moved to his current position with the National Weather Service in 2010. And if I could add also that Jim, as mentioned above, has been the liaison to the Office of Observations, and Kevin Schraub, Jordan Girth, and I have always appreciate his insights and expertise and coordination with the centers has been truly invaluable. Jim, welcome to the Satellite Book Club. We're ready to begin when you are.
Thank you, Brian, for the kind introduction. My title slide's up here. I'm going to advance a little bit. Let's hope everything moves, please. Pretty, please. There we go. An overview. I make some acknowledgments here and disclaimers, so you might be wondering what's with that subtitle. Then just kind of little background slides just sort of set the stage for the discussion. Then finally, I'll talk about, get into data assimilation itself, or a little bit of the basics and you know what we achieve from data assimilation in the, particularly the numerical weather prediction modeling sense. I like to take a broader view thinking of environmental modeling, numerical environmental modeling as we look to the future. Talk about some of the challenges and opportunities I see for future satellite data assimilation. And then I want to point to the Joint Center for Satellite Data Assimilation as kind of the clearinghouse for helping to take advantage of some of those opportunities and meet some of those challenges. And finally, a summary slide. So let's go ahead. Okay, apparently it likes my mouse better than the down arrow, so we're good here. Acknowledgements. First of all, let me just say, really all the material I have here today is borrowed from other people. And that's kind of linked to my disclaimer. You might have noticed in the bio that Brian mentioned, which is accurate. I'm not really a modeling or data assimilation subject matter expert. I work with a lot of those folks and have for years, but my background is really back in the world of instrument scientists with Doppler instruments in particular, with radars and lidars. So, okay. So that leads me into this subtitle. I'm going to the dictionary definition of Catholic, which means including a wide variety of things and sort of an all-embracing point of view. And that really, that's what I'm trying to do here is to give you sort of a high-level generic perspective here. And this is not specific, for example, to any of our sponsoring NOAA programs for the programs of record for satellites, GOES-R or JPSS. And it's not even a particularly NOAA-centric point of view here. So in the background, if any of you have ever heard Dr. Uccellini talk about numerical weather prediction, he likes to use the analogy of a three-legged stool, that you need these elements here of, you've got to have observations, because you can't really, no matter how good a model you create, you understand your atmospheric processes and for that matter your ocean and other surface properties, and you model those as best you can, by having approximate equations that of the processes that govern the behavior and the evolution of the system you're looking at, the atmosphere and ocean. But if you let a model run free with all those approximations in your equations, it doesn't stay accurate very long. So you've got to have observations that both are used to verify and then to adjust your analysis in order to move that model forward in time. And of course, none of this works unless you have adequate high-performance computing to run the model and to process those observations, and the communications to get data in and out effectively, both the data in the sense of the observations, but also the model fields that have to be distributed. So all of those things have to be balanced. If you have a really hot computer and no good science in your model and no observations, it's just a block that sits there, an engine with no wheels and no transmission and or the ability to use the fuel. If you have a lot of observations, you can drown in data but not be able to have much insight from it unless, again, you have good, accurate processes in your modeling system and the ability to assimilate those data effectively, and then the HPC to run all that. And so you always have to watch the evolutionary considerations of those elements. That if you advance one aspect of that out of step with the others, it doesn't necessarily do you any good. You're not able to take advantage of it. So the other thing that changes in time, of course, is we do get better and better at environmental modeling, particularly NWP, and that means over time the requirements of users evolves and rises, and we have greater expectations. And one of the things we have to look to in the future there is the evolution of metrics for environmental modeling. I keep forgetting, okay. So I'll talk a little bit about the basics of data assimilation. I'll just say I borrowed all this material from John Derber lately of NCEP's Environmental Modeling Center. Everything really comes down to one thing here. As you're trying to work your model forward in time, you're adjusting your analysis, and you want to do that, make that adjustment by minimizing a cost function. This is just basic, statistical minimization theory here. So you've got this cost function J, the penalty, that change that you want to minimize as you make an increment to your analysis of from a background state. But you have to consider the observations that are going into that model, and then of course you have to have a forward operator that translates from the model space into the operator space, so that you can make that and back, so that you can make that adjustment. And you've got to have a knowledge of the background error covariances of the model state, as well as of the as observation errors that can be dependent both on the instrument, on the representativeness of those observations that are being made there. And then finally, you've got constraints on for balance and for physical quantities, noise, everything else that go into this. So it's the idea is simple, but the execution of it gets pretty complicated. So really what you're looking here is just to the point of, I'd like you to understand that as you work in a modeling and DA system, bad results are not only due to the quality of your model, but to the conditioning and the state of the cost function. And you also have to consider the computational impacts of this. As you improve your solution technique, you typically do that in ways that cause you to use more computational resources. So you're always trying to balance that because remember, for NCEP and for the users of NCEPs, the model has to run on time. So simply having just to say, oh, I'm going to improve the physics in my model, or I'm going to bring in more observations, doesn't necessarily help you have a model that is going to be run accurately and within the required time for the modeling cycle. Okay. Again, background error is just the important thing here is that this is how we project information from the observations into the variable space. I got to speed up a little bit because I realize I'm going to run into trouble if I don't. Observation errors have two components: the how precisely the instrument can measure itself, that's the instrument error, and then the representativeness error on how well we can simulate those from the analysis variables. And for different observing systems, either of those can be the dominant factor here. Another problem, something you really want to avoid in all of this is to minimize as much as possible correlated error, which can come from both the instrument side or the representativeness error. We have a lot of problems with correlated instruments between observations between the same variable with different instruments or with similar instruments in the same location. For example, notoriously in satellite data assimilation, when we're looking at microwave and infrared sounders, looking at different channels of the same satellite instrument and having correlated noise there. Okay. And sometimes, of course, this can be even worse in terms of the representativeness error because it can be dependent on situation. Okay. Again, in looking at all the observations we bring into data assimilation, you've got to have typically a forward model that simulates the observations from the analysis variables into the observation space. That is, taking, for example, temperature and moisture and pressure and predicting what satellite radiances you ought to see under various circumstances, such as, in the simplest case, clear sky. And so this can range in complexity simply from interpolating, say, winds and temperatures that you have from your analysis into what you predict for the location and time of a radiosonde observation of those same physical variables, or to the again to the radiances via radiative transfer modeling, or to bending angles for something like GPS radio occultation sensors. Okay? If we don't have enough information from the model to simulate those observations, if the model doesn't include adequate cloud information or trace gases, then there'll be observations we can't use here. And I'm making this point for the satellite side of the house because there's often a complaint that why aren't you using more of my very excellent data in your model? What's wrong with you? And this is just one of those realities that you run into in that process. Okay? And finally, you're using all observations together in the data assimilation realm, and that's important because that's the way we get the most self-consistent and statistically reliable solution. It tends to blur credit though and make things a little bit sometimes unsatisfying to the data supplier in that sense. Okay, that constraint term that I mentioned, that contains things that we know about the analysis. Sometimes this is very straightforward. For example, you might say, I know I shouldn't let my temperature go too high in the polar regions. On the other hand, sometimes when you make what seems like a reasonable constraint like that in a statistical sense, again, statistically unlikely things do occasionally happen. That can be a problem for you. Other things, of course, are just simple physics. That is, you're not going to have negative moisture or ozone, for example, in your analysis. Okay. I'm going to skip ahead a little bit more and just say, point out some of the differences between satellite data assimilation and conventional data assimilation. And really, if you talk to a person who works day in, day out in data assimilation, they're going to tell you there's not that much difference, and there's no point in separating what goes on here. You have to take all observations, whether they're so-called conventional data or the remote sense ground-based data such as radar, and you're going to apply the same rules here, the same basic theory for any of this. So we had a lot of arguments when we started the Joint Center for Satellite Data Assimilation, because a lot of people said, well, we should just call it the Joint Center for Data Assimilation, because we're going to do everything as we go through. But there's a political driver for that because of the preponderance of satellite data that we have going into our numerical weather prediction models over the last decades and going forward as well. But some of the differences in application are, of course, we don't get satellite data necessarily at synoptic times the way we do, say, radiosondes. We get a lot of integration in the satellite data. For example, we don't have range resolved, active sensors. Most often in satellite data, we have the way we do, say, with radar. So we have vertical and horizontal smoothing or integration. That's a bit of a challenge at times. The forward models are more complex, the radiative transfer that I mentioned, or radio occultation. And we have biases that tend to be very common in satellite data. Finally, again, there's just a whole lot more satellite data than conventional data, which certainly gives us some practical constraints and kind of drives the amount of time that we spend thinking about satellite data versus conventional data. Okay? And of course, there are some situations where satellite data simply can't be used, at least yet, because of the insufficiency of the current forward models. So we're still working, for example, at all-sky radiance assimilation for microwave and infrared data in the presence of clouds or precipitations, or over land surfaces, which tend to be highly variable and the background changes a lot. We do better, for example, over oceans. Okay. Just kind of summarizing all of this, to optimize data assimilation specifically, you've got to consider all of the above for every model, every data assimilation system, every addition you make to the observation system, and also for computational platforms and configurations. So, there's a lot of simultaneous challenges here. And I guess it begs the question, is all of this worth it? What do we get from our modeling efforts and our DA efforts? Okay, so I'll point out here just a recent example looking at our skill forecast models for several model sets. One is the global forecast system, the other is the global ensemble forecast system, and then finally the NESDIS, the North American ensemble forecast system. And we're looking at this using that beloved anomaly correlation skill score, which maxes out at Unity, as a function of forecast lead time over a number of days here. There's a horizontal line there at 0.6, which is generally considered to be the cutoff point for useful skill being added. That is, if you're getting scores that are consistently above 0.6 and you're adding skill to beyond persistence to the forecast process. And so you want to be able to extend that out as far as you can in time. So at the shortest time scales, at 1 or 2 or even 3 days, you're getting very, very good forecast skill in any of those systems, regardless of what modeling modeling system you're using there. As you go out in time, of course, as you'd expect, forecast skill tends to decrease. Okay? And you can see that then there starts to be a difference between what's going on in the GFS and the GEFS and the NACE. And of course, that's sort of as you expect, because when you take advantage of ensembling, okay, then you have that in the global model. That helps to reduce the uncertainty and removes certain outliers of any particular ensemble member in that arrangement. So over time you see that the skill of the deterministic model decreases relative to the ensemble cases, and then the North American model does ensemble model does even better over time than because of in part because of some of the additional data that are being assimilated. Okay. So that comes to that question, well, what is the impact of the data themselves? So I've taken a kind of an old figure here. This is an ensemble forecast sensitivity to observations impact, and it looks at the 24-hour error reduction in analysis that can be attributed to various components of the observation system here. So this was functional in the global forecast, in the GFS at that time when Dave Groff was working on this. So you have a lot of microwave and sensors in space at that time, also some infrared sounders as well. And you notice that, not surprisingly, because we did have so many AMSUs and ATMS, the biggest total impact we got was from the assimilation of those microwave sounders in polar orbits. Right below that, you see aircraft, winds, and radiosondes as the next biggest contributors. Satellite winds, both polar satellites and also geostationary, providing the next biggest. And then the infrared sensors, AIRS and the OSI, starting to contribute, as well as radio occultation, and going down the list there. I always like to be a little bit careful when we look at this type of metric, because these short-term forecast error reductions don't always lead to longer-term predictability. That's one of the things you have to be careful about. But we can see the general influence of the individual sensors and contributors in this viewpoint. So, just to give you a contrast, and this is a couple years later, but a different model, and using a slightly different, using a tangent linear form of the FSOI in NASA's global model, and you see some interesting, differences in results here. And it's where, for now, the geostationary winds are the biggest single contributor to forecast error reductions, followed by radiosondes, then the AMSU and ATMS, then infrared sounders. So you see a lot of the same things at the top, but the relative positions have changed a little bit, which just is to be illustrative of the fact that different models and different data assimilation systems, the 4D VAR that's being used for driving the GEOS-5 versus the 4D ensemble approach, hybrid approach that's being used with the GFS at that time, do give you different outcomes. So what are some challenges and opportunities for the future? Well, the NSET production suite is evolving. Of course, we're looking at we have and will continue to have a whole suite of models that really range in terms of time, of going from minutes for warnings and alerts and watches in the terms of hours, going out to years and for seasonal and outlooks and beyond, interannual outlooks. Okay, and the benefits, of course, of each of those that kind of apply by by different timescales, saving lives and properties for warnings and alerts, or looking at the environmental impacts and how those affect people's health on timescales of years for for climate type outlooks. As we do that, the whole national prediction system is transferring into the unified forecast system, the UFS applications. I borrowed this slide from Vijay Talapragada earlier, and the thing about this is you have the same structures, the same functions driving a whole range of modeling applications. So if you look at all of those applications on the outside there in the blue, each of those is being pushed with the same modeling physics, the same dynamic core, the same data assimilation pieces that you see, for example, over there at the left, the so-called JEDI iota for the future. Okay. Think about future observations too, as well as the future of the DA and modeling system. I could go beyond satellite systems. There's a lot of talk these days about crowdsourced observations and whatnot, but just sticking to satellites here. What do we have coming up? We have the MEDOP second generation and NESDIS third generation, which will bring a hyperspectral IR sounder into a geo orbit for operationally, and that's expected that we'll have those from other systems as well, including we hope in the next generation US geo system or geo extended orbits. Okay. Of course, we'll have that, as I say, the GeoXO, and of course we have JPSS and its follow-on still continuing. There's a lot of emphasis now on small sats and CubeSats, which will carry, which will come online quickly, carrying smaller payloads, but perhaps more specific ones, such as microwave sounding units that would be, or microwave sounders to complement those on our larger programs of record. Commercially procured observations for sounders. We already have currently commercially procured radio occultation sounders, and that's we have those being used operationally. If we start looking at sounders, though, that is microwave and infrared sounders, that'll become even more of a challenge because the radio occultation data tend to be, because they're tied to atomic clocks, you have very precise measurements. They don't vary so much from platform to platform. You don't have spectral response functions to consider, but that would become a different issue when if we have commercially procured sounders rather than the traditional government or partner ones. So we're going to have this challenge to exploit more data from more sources and more varied sources, and for that matter, on probably processed on a lot of different more varied systems, for example, including the cloud. So there I step in and say one of the keys to dealing with all of this for us is going to be to continue to exploit the Joint Center for Satellite Data Assimilation, which is about 20 years old now. And its mission really is to accelerate and improve the use of both research and satellite data in our environmental models, analyses, and models. This is not just a NOAA affair. This is really a test bed that for NOAA that's with participation from OAR and NESDIS, as well as the Weather Service, but also working with NASA for their satellite and modeling expertise, and with working with the operational, the development and operational aspects of the Navy and the Air Force for their weather modeling needs. Okay. Over time, the Joint Center itself has evolved. We used to kind of work sort of in this on the left-hand side. We had a lot of overlap. We had a lot of individual efforts all going on on the subject of satellite data assimilation for NWP. And we had a lot of working groups, which became talking groups. It's very hard to measure progress. In the last 5 years, we've moved from that virtual center approach to a distributed center where we have a core staff that resides in Boulder, and we have project leaders who work with dedicated staff or so-called in-kind staff in each of the participating centers. And those in-kind staff which would be the smaller pink eggs you see inside the blue eggs can be federal employers, they can be contractors, typically partial FTEs, but all again working on common projects and kind of making the responsibility be for success be more directly visible and accountable. Okay. We've gone from a waterfall to an agile working practices for development, so that you're getting increments of work done with fast feedback, instead of waiting, I do part A, step B, step C, step D, I get to the end and find out that things don't work, and then I have to go back to the beginning. Working much more in a collaborative environment on all these projects so that participants across all those partner agencies and centers can access the same source code and contribute to it on a regular basis. Having software quality standards, coding standards, and which helps both the quality but also pushes towards having more portable code. That's part of our testing here. We have something called the JEDI product. This is the Joint Effort for Data Assimilation Integration. That's really become the centerpiece of all of this, and will become the centerpiece of the data assimilation system for all of the partners involved, including NOAA, but also for our DoD partners. Okay. So one of the things that we do here with the JEDI approach is we create interfaces to a whole host of modeling systems: Neptune for the Navy, the FE3GFS for NOAA, GEOS for NASA, for example. Won't go through the whole list because there isn't time. But again, we have all of those linked into interface to an object-oriented prediction system where changes, where we become more model independent than we've been in the past. And that in turn is linked to other pieces of common software so that we can use these across all those modeling systems. We have the system agnostic background error representation, the UFO, the unified forward operator, so that again you can have get the forward operators for a multitude of satellite and, for that matter, non-satellite observations readily available for all of those models. For years we've been developing and using the CRTM, that's the Community Radiative Transfer Model, which is one part of that UFO there. So the abstract interfaces are made so that we don't have to have a single monolithic set of code that has to be changed for each of the applications and models. So the high-level objectives of this are through our OBS project, we have observation operators available, as well as access to observations, going into the use of AI for processing in order to increase the speed of that, particularly for radiative transfer modeling. We have applications for the JEDI algorithms for global NWP and actually all sets of applications of NWP and other models as well, going into coupling for the atmosphere, the oceans, waves, ice, land surface, and atmospheric chemistry, and pushing those applications into real-time JEDI development. Okay. One of the things we try to do here is to make sure that as we develop JEDI, we can pass the so-called graduate student test, which is that somebody who's not an insider, but who is an intelligent and scientifically and computer literate colleague on the outside can download and run elements of the code and make experiments and then submit tickets in new code improvements back in a relatively short period of time. We say an afternoon, but but typically in a week or less. So we're again, what we've done in creating the JEDI is really to use modern tools and practices in order to be very broad and to take advantage of the not just the expertise in the participating agencies of the Joint Center, but in the academic and private sector communities as well. Okay, we have a lot of community engagement and support. Just going through a long list of these. Typically, you see that we have our annual symposium as part of the AMS annual meeting. That'll be hybrid this year, I guess. Last year it was virtual. Before that, always face-to-face. We have developers workshops for different aspects of this, the JEDI and the CRTM. And we also have dedicated training, the so-called JEDI academies, a number of those that have been held. Now we've been actually starting to do this virtually. We had a JEDI short course as part of last year's AMS, or this year's actually, I guess, AMS meeting. And this is just some nice photos of different groups at those various events. Okay. So in summary, I just point out that data assimilation is central to or a central piece of successful environmental modeling. Satellite data constitute the vast majority of the observations available for NWP and other environmental modeling. Our future trend is going to be more satellites, more sensors, more observations, and more variability, and using more models and applications and more coupling between those models and applications, and that the Joint Center and JEDI will be critical for exploiting these trends. How am I doing on time here? Okay. Guess we're okay. All right, that ends my talk. So I'm really ready for questions at this point. And I thank you for your attention.
Yeah, excellent. Thanks, Jim. I really appreciate it. And I found it really interesting on my end being, more on the operational side to kind of get some of those details on the data assimilation. So my name is Steve Flegel. I'm the SU at the NWS Aberdeen. So I'm the facilitator for this week. So after this, since we've had this talk, please take a little bit of time, and if you have any questions for Jim, throw them into the chat. Especially if anyone from the field offices or regional headquarters, we really like to get some of those questions from you. I saw Lee just posted into the chat room the survey, so if you have any feedback on the Satellite Book Club itself, or this session, feel free to fill out that survey. As you can see on the screen, as we go to next week, on Thursday, October 28th, please note that there will be a change of time for next week. This week, or normally they're at noon. Next week it will be at 1 p.m. So 1 p.m. on Thursday, October 28th. We'll have Dr. Chad Gravel, the Techniques Development Meteorologist from Southern Region Headquarters, and he'll discuss the usage of GOES mesosectors. And then also want to encourage you to contact the Tower S team, Lee Byerly or Kashad Bowman, for any questions that you have about the Satellite Book Club, or configuration of satellite products. I know, myself and our ITO here at the Aberdeen office, we've contacted them numerous times as we've gone through installs or updates, that type of thing. They've always been really helpful. So, definitely reach out to them if you have any questions. So while we're waiting for some, questions to kind of come in, I do have one here that I can ask you, Jim. So what do you regard as the single biggest challenge to effective satellite data assimilation within the next decade, and why?
Thanks. I'll give two answers to that, because one of them is we call there's this a technical challenge, which simply has to do with the pace of change. You have so many new satellites and coming online, and the prospect of having a lot of commercially sourced data coming on, and I'm not sure that the commercials sector is really good at building these instruments and flying them but that doesn't necessarily mean that you can get very good quality data and not necessarily have all the metadata you need, for example, in order to take advantage of them. Not through any ill intent, but just through lack of experience and understanding of that need. And again, the pace with which those are coming, I think, is going to be huge. The second piece is a little more in terms of sociological in the breadth of our community, and I think it has to do with having realistic expectations, across the breadth of our enterprise. As I mentioned, I'm an instrument guy and a satellite guy, and I know that from years of working in NESDIS that one of the things we want to see happen is we fly an instrument, we prove a sensor, and we want to see those data used quickly, and we want to see them used at 100% of those data in use. From the modeling point of view, that isn't necessarily as meaningful. If you use more data but you don't improve your forecast metrics, what's the point of putting more data in there? So you have to make sure you get there. And even as you improve skill scores from our typical metrics, we're reaching headroom, or reaching the bumping into the or running out of headroom is what I'm trying to say, by virtue of by some of those metrics. How meaningful is it to push the 500 millibar anomaly correlation skill scores? When you're going from over from 0.9 to 0.91, it may be statistically significant but not practically significant. And when I think about forecasters in the field at forecast offices and at centers, you're saying, well, yeah, we know what we need to improve aspects of our forecast, but they're not necessarily the ones that are reflected by the metrics that we currently use. So we might need to have a whole new sets of metrics and then see how our satellite data as they're assimilated impact those.
Yeah, thank you, Jim. Just a follow-up, which it kind of ties into a little bit of your second part of your response there, but can you tell us where some of the assimilation improvement activities that are now underway are likely to bring the latest or greatest benefits to modeling, that type of thing? Is it like precip QPF or precip type microscale features, that type of thing? Or are the assimilation improvements more broadly targeted or aimed at improving the overall model performance?
They tend to be more broad, but I think we have to start looking in terms of how we attack those metrics like that. But there is a link here. For example, in looking at precipitation, I think looking at how well we assimilate cloudy and precipitation affected radiances, which we don't do well now. That's something that as we improve that aspect of the assimilation, you would hope that would bear on our QPF forecasting in the future.
Thank you.
I see a question from Bill Schoberg. I love chat. Yeah. This is one of the best things on here. Bill Schoberg is asking, has been any progress to shorten the time needed to assimilate new data sources into products? And now that I've not got the part about products because I don't normally do data sources into products, but data sources into the forecast process. There has been a lot of progress in that sense. I mean, from starting with SNPP and through J1 and with the GOES-R series of geosatellites, we've gotten under that 2-year and then 1-year threshold for getting for microwave radiances, infrared radiances, and winds into operations. Now, part of it is technique. Part of it is, I think, trying to beat down risk aversion. The somewhat shorter testing that's involved. We've been very rapid in terms of new radio occultation data sources, starting with Cosmic 2, but also with the ComSat 5 from Korea, and with the more recently with commercially sourced radio occultation data from both the Geo-Optics Corporation and then most recently with a new delivery order from Spire. But radio occultation had that advantage of having a certain absolute calibration, which doesn't mean they're perfect, but that does not vary as much from one platform to another. That makes that a little bit easier. I don't know if we'll be able to be as quick in transitions with other small sat type observations. And so I think I did answer Bill Schoberg's question.
Okay. Yeah, and then there's one other one. We'll try and sneak it in here before the end from Michael Jamalkowski. He had a question on your slide. I think it was slide 17 with the impact of the data used on the NASA GEOS-5 model. He mentioned that the GOES are ABIs not listed, realizing that soundings are derived and not directly measured. So he was wondering why it wasn't listed. Was there zero impact, or was it an old graphic?
That's an old graphic, and so if they're not being used in that particular run. Okay, they're assimilating GOES only as they're assimilating the wind product, but not the radiances there. We still don't assimilate GOES ABI radiances yet in the NCEP, in the GFS either. And that's one of those things we need to push.
Excellent. I think that's all I see for questions. So I think I'll turn it over to Brian for the final remarks.
All right, terrific. Thank you, Stephen, for moderating today's session. And also a final thank you to Jim for a really informative brief on assimilation. Something of ground we don't often cover here at the Satellite Book Club, but an interesting related topic. In closing, I just want to give everyone a friendly reminder, as Stephen mentioned, that Chad Gravel will be here next week, Satellite Book Club Seminar Series. So we'll be holding that meeting an hour later than usual, 1 o'clock Eastern Time, but we hope you can join us then. That's it for today. Thanks everyone for joining, and enjoy the rest of your day.